The universe has laboratories where physics itself begins to fracture. We are about to tour 20 extreme objects that push reality to its breaking point. By the end, you will grasp how these cosmic puzzles are forcing a revolution in our understanding of everything. What happens where gravity becomes infinite, or where a star is made not of matter, but of pure force? These are not just distant curiosities. They are the ultimate tests for every law we think we know, from Einstein's relativity to the quantum rules that govern particles. Studying them is our only way to glimpse a deeper truth hidden in the fabric of space and time. What do you believe lies beyond the edge of our current physics? Our journey begins not with a gentle curiosity, but with a cosmic monster of pure force. A magnetar is the universe's ultimate magnet, a star so dense a single teaspoon of its material would weigh billions of tons. But that staggering density is not its most terrifying feature. It is the magnetic field, a quadrillion times stronger than the one that guides our compasses. To understand that scale, picture a magnet so powerful it could erase every credit card on Earth from halfway to the moon. This is not science fiction. It is the remnant heart of a massive star that died in a cataclysmic supernova. When that star collapses, its already intense magnetic field gets wound up, twisted and compressed into a configuration of pure energy that defies our everyday experience. Under that unimaginable pressure, the rules change. The magnetic field becomes so strong it can distort the very shape of atoms, stretching them into long, thin needles. It can tear apart matter from thousands of kilometers away, ripping electrons from their orbits in a violent process. The crust of a magnetar, a crystalline shell of iron nuclei under immense strain, is not a stable place. Occasionally, it cracks. These starquakes release more energy in a tenth of a second than our sun will emit in 100,000 years. For that brief, blinding moment, a single point in space outshines an entire galaxy. Magnetars push the known laws of electromagnetism and material science to a breaking point we cannot recreate. They exist as natural laboratories, forcing us to ask what matter truly becomes when subjected to forces that rewrite its most fundamental rules. If a magnetar's power feels like the universe shouting, then a black hole is the moment it falls utterly silent. This is where space-time itself tears. At its heart lies the singularity, a point of infinite density where the known laws of physics cease to function. According to Einstein's general relativity, gravity here becomes so overwhelming that the fabric of reality curves into a one-way path. This creates the event horizon, a boundary of no return. Cross it, and not even light, the fastest thing in existence, has the energy to climb back out. It is the ultimate point of forgetting, a cosmic vacuum cleaner that does not just consume stars and gas, but consumes our very understanding. Yet, these objects are not quite as simple as they seem. The brilliant physicist Stephen Hawking proposed a startling idea that black holes are not entirely black. Through a subtle quantum mechanical effect at the very edge of the event horizon, they can slowly leak radiation and evaporate over incomprehensible timescales. This Hawking radiation creates a profound paradox. It pits the smooth, deterministic world of Einstein's gravity against the fuzzy, probabilistic rules of quantum theory. One set of laws says information swallowed by a black hole is lost forever. The other suggests it must be preserved. This conflict is not a minor academic debate. It is a fundamental confrontation, revealing that our two most successful descriptions of reality are fundamentally incompatible when pushed to this extreme. A black hole is not merely an object in space. It is a question mark carved into the universe, forcing us to ask what truly happens when space-time reaches its breaking point. But what if the collapse of a star stops just short of forming a black hole? You get an object even more alien and dense than a magnetar. A neutron star is essentially an atomic nucleus the size of a city. When a giant star runs out of fuel, its core collapses in a violent supernova. The outer layers blast away in a spectacular cosmic light show, but the core is crushed inward by its own immense gravity. The pressure becomes so overwhelming that it forces protons and electrons to merge, creating a sphere composed almost entirely of neutrons. Picture taking the entire mass of our Sun and squeezing it into a sphere only about 12 miles across. The density is almost beyond comprehension. A single sugar cube of this material would weigh as much as every human being on Earth combined. This creates a surface gravity 100 billion times stronger than what we feel on our planet. If you could stand on its surface, which of course you cannot, the force would compress you into a film of atoms thinner than paper. Even the landscape is flattened by this power. Any theoretical mountain on a neutron star's crust would be no taller than a millimeter. These stars are not just static balls, however. Many of them spin, and some rotate hundreds of times every single second. When they are aligned just right, their powerful magnetic fields funnel beams of radiation from their poles. As the star spins, these beams sweep across space like a cosmic lighthouse. From Earth, we see this as a precise, repeating pulse of radio waves, earning them the name pulsars. Their ticking is more accurate than the most advanced atomic clocks we can build. Yet the true mystery lies within. The interior of a neutron star is a place where the strong nuclear force, which glues atomic nuclei together, is pushed to its absolute limit. Under pressures that make the core of a hydrogen bomb seem trivial, matter is forced into states we can only theorize about. Physicists suggest the core may contain layers of exotic nuclear material with strange shapes, whimsically called nuclear pasta. Deeper still, the neutrons themselves might break down into a soup of their constituent particles, a sea of free quarks. A neutron star is a cosmic pressure cooker, a natural laboratory for physics we cannot hope to recreate on Earth. By studying them, we are essentially reading the universe's own manual on the most extreme states of matter imaginable. The universe's laboratories are not only places of unimaginable pressure, but also of exquisite, delicate balance. A white dwarf is the final, brilliant sigh of a star like our own Sun. After it has exhausted its nuclear fuel and shed its outer layers, what remains is a core of incredible density, compressed by gravity into a sphere roughly the size of Earth. Yet within that sphere is packed the entire mass of a star. This creates a bizarre reality where a single teaspoon of white dwarf material would weigh several tons here on our world. But unlike the crushing collapse of a neutron star, this object finds stability in a strange and fundamental rule of the quantum world. It is held up not by the fiery furnace of fusion, but by a ghostly force called electron degeneracy pressure. This is a direct consequence of a quantum law that states no two electrons can occupy the same quantum state. As gravity tries to squeeze the star's core ever smaller, these electrons are pushed closer and closer together. Eventually, they simply have nowhere left to go. They resist further compression not through heat or chemical bonds, but through this fundamental prohibition, creating an outward pressure that finally balances the inward pull of gravity. It is a perfect, silent stalemate between the cosmic force that builds stars and the subatomic rules that govern particles. Yet this balance has a strict limit, discovered by the brilliant astrophysicist Subrahmanyan Chandrasekhar. The Chandrasekhar limit, about 1.4 times the mass of our Sun, is the maximum weight a white dwarf can support. If it crosses that line, perhaps by pulling material from a companion star, the quantum pressure of the electrons is overwhelmed. The delicate balance shatters in an instant, leading to a catastrophic collapse that can trigger a titanic supernova or birth an entirely new neutron star. White dwarfs are therefore cosmic time capsules and silent prophecies. They are the future resting place for over 90% of all stars in our galaxy, including our own sun billions of years from now. They will slowly cool over eons, fading from a white-hot ember to a cold, dark crystal of carbon and oxygen, a diamond the size of a world drifting through an endless night. In their serene persistence, they show us a universe where the tiniest rules of quantum mechanics stand as the final defense against total gravitational collapse. A fragile frontier where physics is tested not by raw power, but by perfect, precarious equilibrium. But what happens when even the neutrons in a star's core can no longer withstand the pressure? This leads us to a theoretical frontier, a hypothetical middle ground that could rewrite the textbooks. A quark star is a concept born from pushing our theories to their absolute limit. We know that inside a neutron star, matter is crushed into a sea of neutrons. Yet physicists suspect that at a certain, even more extreme threshold, those neutrons themselves might shatter. They would break apart into their most fundamental components, a swirling soup of free quarks. In our everyday world, quarks are never found alone. They are forever bound together in groups of 2 or 3, forming the protons and neutrons that make up atoms. This confinement is a fundamental rule of the strong nuclear force. But in the heart of a collapsing star, the pressure might become so unimaginably vast that it overcomes this rule, liberating the quarks from their bonds. This would create an entirely new and potentially stable state of matter known as strange matter. The name comes from a particular type of quark, the strange quark, which could become a dominant component in this exotic soup. The implications are startling. Some models suggest that strange matter could be the most stable form of matter in the entire universe. If that is true, a single drop of it could, in theory, act like a cosmic contagion. Upon contact, it could convert normal atomic matter into more strange matter, triggering a chain reaction that would transform an entire object from the inside out. While this sounds like the premise of a science fiction story, it is a serious theoretical possibility that emerges from our equations. The hunt for a quark star is therefore a hunt for the ultimate state of confinement. Finding one would be a direct, spectacular validation of quantum chromodynamics, our theory of the strong force that binds the atomic nucleus. It would show us what matter becomes when it is squeezed beyond the neutron star phase, but before it vanishes forever behind a black hole's event horizon. These objects, if they exist, are the universe's ultimate pressure cookers, laboratories where the rules of particle physics are tested under conditions so severe they set the quarks themselves free. Their discovery would not just add a new entry to a catalogue of cosmic objects, it would open a window into a realm of physics we have only ever dreamed of probing. The idea of a star made from solid matter begins to feel almost quaint. What if a star could be woven not from atoms, but from the very fabric of force itself? This is the ethereal concept of a boson star. In our familiar world, stars are immense balls of plasma, powered by nuclear fusion. But the universe's building blocks are divided into 2 fundamental families. Fermions, like protons and electrons, are the particles of matter. They obey a strict rule that prevents them from crowding into the same space, a principle that gives white dwarfs and neutron stars their structural integrity. Bosons are the other family. They are the messengers, the carriers of forces. The photon, the particle of light, is a boson. So is the Higgs boson, which gives other particles their mass. And crucially, bosons do not follow that exclusion rule. They can all pile into the exact same quantum state, a phenomenon called a Bose-Einstein condensate. In theory, a vast cloud of a yet undiscovered, stable boson could be pulled together by its own gravity, condensing into a giant, coherent object, a star made of pure force field. It would have no nuclear furnace at its heart. It might not even emit light in any conventional way. A boson star could be completely invisible, a massive ghost in space detectable only by the way its gravity bends the light from objects behind it, acting as a perfect gravitational lens. Or it could be translucent, a faint, shimmering sphere of potential energy. This pushes particle astrophysics into a profoundly strange new territory. It suggests that the universe's hidden architecture, the dark matter that binds galaxies together, might not be made of unknown particles of matter, but of diffuse or clumped fields of force. If dark matter consists of a type of boson, then boson stars could be scattered throughout galactic halos, invisible engines of gravity shaping everything we see. The search for them is not a hunt for a bright object in a telescope. It is a forensic investigation of gravity's subtle fingerprints, a challenge to find structures that are woven from the universe's most fundamental threads. They represent a possibility where the distinction between a particle and a field, between matter and force, completely dissolves, revealing a cosmos built from concepts we are only beginning to grasp. Our cosmic journey now takes us from the heart of stars into the profound and lonely darkness between them. Rogue planets are the dark wanderers of the galaxy, worlds that have been violently ejected from their home solar systems. Imagine a planet like Jupiter or Earth, not orbiting a star but cast adrift into the interstellar void. It is a permanent night, untethered from any sun, where surface temperatures can plummet to just a few degrees above absolute zero, the coldest possible temperature in the universe. This is not a gentle cooling. It is a deep freeze that would make the icy poles of Pluto feel balmy by comparison. Yet these worlds are not necessarily dead. Some may possess thick, insulating atmospheres of hydrogen or methane that trap the faint residual heat from their violent formation, creating a thin thermal blanket against the endless cold. Others, with rocky or icy compositions, might harbor deep subsurface oceans. These hidden seas could be kept liquid not by sunlight, but by the internal warmth of radioactive decay in the planet's core, or by the relentless gravitational kneading from a large moon, creating tidal friction that generates heat from within. These possibilities force us to completely rethink the very idea of a habitable zone. We have long defined it as that narrow band around a star where liquid water can exist on a planet's surface. But rogue planets shatter that cozy definition. They tell us that habitability might not be a gift bestowed by a nearby star, but an internal property, a spark of geothermal or geochemical potential that a world carries within itself, independent of sunlight. This realization pushes our models of planetary formation to their breaking point. It suggests that the early lives of solar systems are far more chaotic and violent than we once believed, with gravitational pinball games that can fling entire worlds into the abyss. The existence of these dark wanderers implies a staggering hidden population. For every star-bound planet we see, there could be dozens, even hundreds, of these lonely nomads drifting unseen through the galactic night. Their silent journey challenges our deepest assumptions. If life can take hold in the sunless, frozen depths of a rogue world's underground ocean, sustained only by chemistry and planetary warmth, then life is not a delicate miracle confined to rare, Goldilocks orbits. It becomes a potential property of matter itself, a stubborn, resilient force that could thrive in the most unexpected and hostile corners of the cosmos. The galaxy may be filled not just with islands of life around stars, but with dark, independent arcs sailing silently through the eternal night. Some stars do not drift quietly through the cosmic dark. They are shot from a galactic cannon. Hypervelocity stars are stellar projectiles, flung from the very heart of the Milky Way at speeds exceeding 1 million miles per hour. To move that fast is to defy the very concept of an orbit. It is a velocity so great that these stars are not merely traveling through the galaxy. They are in the process of abandoning it entirely, destined for the lonely intergalactic void. Their origin story is written in gravity's most violent script. At the center of our galaxy sits Sagittarius, a star, a supermassive black hole millions of times heavier than our Sun. When a binary star system, two stars orbiting each other, wanders too close to this gravitational monster, a cosmic slingshot event can occur. The black hole's immense gravity can tear the pair apart, capturing one star into a tight orbit while violently flinging its companion away at a staggering fraction of the speed of light. It is a gravitational three-body interaction of catastrophic precision. The ejected star becomes a runaway, carrying with it the kinetic signature of that primordial encounter. This makes hypervelocity stars more than just celestial curiosities. They are forensic evidence. By tracing their paths backwards through space, astronomers can map the invisible gravitational landscape of the galactic center. Each trajectory is a scar, a line drawn by the black hole's overwhelming influence, allowing us to probe regions so crowded and chaotic that direct observation is nearly impossible. These stellar cannonballs test the limits of orbital mechanics on a scale we can never simulate. They show us that the galaxy's core is not a placid place, but a dynamic engine capable of accelerating entire suns to velocities that break the bonds of the Milky Way itself. Their silent, speeding journeys ask a profound question. What other unseen forces lurking in the hearts of galaxies are sculpting the cosmos through acts of gravitational violence we are only beginning to witness? Gravity, as we know it, is a force of relentless attraction. But what if we could reverse its pull? To build the cosmic shortcuts of our imagination, we need a material that does not just resist gravity, but actively pushes against it. This is the realm of exotic matter and negative energy, a theoretical substance that would possess negative mass. If you pushed an object with negative mass, it would move toward you instead of away. Its gravitational field would repel everything around it, creating a kind of anti-gravity. This is not merely a strange idea. It is a strict mathematical requirement for some of the most tantalizing concepts in theoretical physics. To hold a traversable wormhole open, preventing its throat from instantly pinching shut, you would need to line it with this exotic matter. To construct an Alcubierre warp drive, compressing spacetime in front of a ship and expanding it behind, you would require a ring of material with negative energy density to bend the fabric of reality in just the right way. For decades, this seemed like pure mathematical fantasy, a clear sign that such technologies were forever forbidden by the laws of physics. But then, a curious quantum glimmer appeared. In the microscopic world, empty space is not truly empty. It is a seething quantum foam where virtual particles constantly blink in and out of existence. Place two perfectly smooth, uncharged metal plates extremely close together in a vacuum. The plates can restrict the types of quantum fluctuations that can appear in the gap between them. This creates a subtle pressure difference, and the plates are pushed together. This is the Casimir effect, a verified phenomenon where the energy density between the plates is effectively lower than the energy of the surrounding vacuum. In a very specific, fleeting sense, this region exhibits negative energy. We have not created a block of negative mass, but we have manipulated the quantum vacuum to produce a shadow of the effect we would need. This tiny demonstration pushes quantum field theory to its philosophical limits. It asks whether these microscopic quantum permissions could ever be scaled up into a macroscopic, stable configuration. Could the universe's rulebook, which allows for such fleeting exceptions, be engineered into a permanent feature? Or is there a deeper principle, a cosmic censorship, that forever prohibits assembling enough exotic matter to build a gateway? The pursuit is not really about building starships. It is a fundamental probe into the structure of physical law. By asking if exotic matter can exist, we are asking if the universe contains hidden levers within spacetime itself, waiting for a civilization clever enough to find the combination. The universe's earliest moments were not a smooth unfolding, but a phased transition of staggering violence. Cosmic strings are the scars from that birth, one-dimensional cracks in the fabric of space-time itself. Picture the early cosmos cooling from an unimaginably hot, unified state. As it expanded and cooled, the fundamental forces we know today, gravity, electromagnetism, the nuclear forces, began to separate out or break symmetry. Theorists suggest this process could have been imperfect, leaving behind defects frozen into the structure of reality. A cosmic string is such a defect, but of a scale that defies intuition. It is hypothesized to be thinner than a proton, yet so dense that a single inch of it could weigh more than Mount Everest. This creates a gravitational footprint like a razor slit through the cosmos. Space-time is warped along its infinite length, creating a region where the geometry of the universe is fundamentally torn. If one were to pass between Earth and a distant galaxy, its extreme gravity would bend the light from that galaxy, potentially creating a perfect double image in our telescopes, a ghostly cosmic mirage. These strings are not static scars. Under their immense tension, they could whip and vibrate at a significant fraction of the speed of light, snapping off loops or creating cusps that would ripple space-time itself, broadcasting bursts of gravitational waves across the universe. Their potential discovery is not merely about finding another odd object. It is a direct test of our boldest theories about the universe's origin, specifically grand unified theories that attempt to describe all forces as one. Finding a cosmic string would be like discovering a fossil from the first trillionth of a second after the Big Bang. It would provide a physical, observable clue to the symmetry-breaking events that ultimately determined the laws of physics as we experience them today. They are threads woven from the universe's deepest history, and if we could find one, we could literally trace a line back to the moment everything began. Galaxies are not isolated islands of stars. They are held together by a ghost. Every spiral and elliptical we observe is embedded within a vast, invisible sphere, a halo of dark matter that extends far beyond its luminous edge. This is the universe's hidden skeleton, an architecture of mystery that makes up over 85% of all matter in the cosmos. We know it is there only by its gravitational handshake. The stars at the outer edges of galaxies rotate far too quickly. According to the visible mass of gas and stars, these outer stars should be flung into the intergalactic void by centrifugal force. Yet they are not. Something with immense gravitational pull, something we cannot see, is holding the entire structure together. That something is the dark matter halo. It provides the gravitational glue that prevents galaxies from tearing themselves apart, acting as a cosmic scaffold upon which the luminous universe is built. This pushes our understanding of particle physics to a profound breaking point. The Standard Model, our catalogue of every known particle and force, has no candidate for what dark matter could be. It does not absorb, emit, or reflect light. It seems to interact with normal matter only through the whisper of gravity, passing through planets and people as if they were not even there. This has forced physicists down two radical paths. The first is the hunt for a new particle, perhaps a weakly interacting massive particle that was forged in the Big Bang and now permeates all space. The second, more controversial idea is that our theory of gravity itself, Einstein's magnificent general relativity, might require modification on the scale of galaxies. Both possibilities represent a fundamental crisis. Either the universe is filled with a shadow substance we have never detected, or our most successful theory of gravity is incomplete. These invisible halos are not passive containers. Their gravitational influence dictates the large-scale structure of the cosmos, guiding how galaxies cluster and flow in great cosmic webs. To map them, astronomers must become detectives of the unseen, watching how their gravity bends the light from more distant galaxies, a phenomenon called gravitational lensing, or studying the faint whispers of radiation from the hot gas trapped within their pull. The dark matter halo is the ultimate cosmic paradox. It is the dominant architectural feature of the universe, the framework for everything we see, and yet it remains utterly, frustratingly transparent. To solve its mystery is not just to identify a missing component. It is to answer a question that strikes at the core of our reality. What is the universe truly made of? The dark matter that holds galaxies together is a silent force, but the cosmos also screams. A gamma-ray burst is the universe's loudest, most violent shout. In a span of seconds, sometimes less, a single point in space can unleash more raw power than our sun will generate across its entire 10 billion-year lifespan. It is a flash of pure, concentrated fury that briefly outshines every star in its home galaxy combined. The cause of such an apocalyptic release is a stellar death of unparalleled violence. The leading theories point to two cataclysmic births. The first is the collapse of a truly massive star, dozens of times heavier than our sun. When its core finally runs out of fuel, it does not just collapse into a neutron star. It falls completely, catastrophically, into a newborn black hole. As material swirls inward at nearly the speed of light, powerful magnetic fields channel some of it into twin jets that blast outward from the poles, punching straight through the dying star's outer layers. These jets are not just streams of hot gas. They are relativistic beams where particles are accelerated to over 99.99% of the speed of light. When these ultra-fast jets plow into the surrounding interstellar gas, they create colossal shock waves. It is within these titanic collisions that the gamma rays themselves are born, in a fireball of high-energy radiation that marks the most powerful explosion since the Big Bang. The second type of burst comes from an even more exotic merger. When two neutron stars, those ultra-dense city-sized remnants, spiral together and finally collide, they create a spectacular kilonova. This violent union sprays neutron-rich material across space, forging heavy elements in a rapid process of nuclear synthesis. It is in these fleeting, universe-shaking moments that much of the cosmos's gold, platinum, and other precious heavy elements are thought to be forged. A single such event can seed an entire galaxy with the raw materials for future planets and, potentially, life. This makes gamma-ray bursts far more than just cosmic fireworks. They are the universe's ultimate natural particle accelerators and foundries, operating at energy scales we could never hope to replicate on Earth. They test the absolute limits of our models for relativistic hydrodynamics, the behavior of matter moving at a significant fraction of light speed, and the very process of nucleosynthesis that builds the periodic table. By studying their brief, brilliant flash and the long-lasting afterglow that follows across other wavelengths, astronomers are not just watching an explosion. They are using these events as beacons, illuminating the gas and structure of the distant, early universe. Each burst is a message from an era when galaxies were first assembling, carried to us on a wave of the highest energy light the cosmos can produce. The universe's most resilient worlds orbit the dead. Pulsar planets are cosmic paradoxes, existing in the graveyard of a star's violent end. They circle a pulsar, the rapidly spinning, intensely magnetized core of a neutron star that survived a supernova. This environment is one of perpetual, lethal twilight. The planet is bathed not in warm sunlight, but in a relentless torrent of X-rays, gamma rays, and radio waves from the pulsar's powerful beams. The gravitational tides are immense, likely stretching and squeezing the world's very structure. It is a realm where our traditional ideas of a stable, life-nurturing orbit are not just challenged but completely inverted. The discovery of these worlds was itself a shock to astronomy. The very first planets ever found beyond our solar system were not in a place anyone expected. In 1992, astronomers detected tiny, rhythmic wobbles in the clockwork signal of a pulsar known as PSRB 1257+12. Those subtle variations revealed the gravitational tug of not one, but three worlds orbiting this stellar corpse. This finding was revolutionary. It proved planets could exist in the most hostile environments imaginable, surviving the apocalyptic supernova that forged the pulsar itself. Their origin story is a profound mystery. One possibility is that they are second-generation planets. The supernova that destroyed the original star may not have completely vaporized all its planets. Perhaps the inner worlds were obliterated, but outer gas giants survived, their orbits thrown into chaos before settling into new, tighter paths around the pulsar. Another, even more astonishing idea is that these planets formed from the ashes. The supernova would have ejected a vast cloud of heavy elements, a rich debris disk of stellar material. From this disk of destruction, entirely new worlds could have coalesced, born directly from the remnants of the old star's death. This pushes our models of planetary formation to an extreme we never anticipated. Could a new solar system be forged from the funeral pyre of the old? The implications for life, however, seem grim. The surface of such a planet would be sterilized by the pulsar's intense radiation, a constant barrage that would strip away any atmosphere and scour the rock. Yet, as with rogue planets, habitability might retreat to the interior. A world with a thick, icy crust or a rocky mantle could shield a subsurface ocean from the radiation above. The energy to keep it liquid would not come from a sun, but from the fierce gravitational kneading of the pulsar's tides, creating internal heat through constant friction. While this stretches the concept of a habitable zone to its absolute breaking point, it underscores a powerful cosmic truth. Planets are survivors. They can endure stellar cataclysms, be born from chaos, and cling to existence in environments we would deem utterly inhospitable. Pulsar planets are not just oddities, they are monuments to persistence, proving that where there is gravity and material, the universe will find a way to build worlds, even in the heart of a perpetual storm. A star can sometimes hide a secret heart. A Thorne Żytkow object is one of the universe's most peculiar hypothetical creations, a stellar chimera where two radically different states of matter are forced to coexist. Picture a vast, bloated red supergiant star, so large its outer atmosphere would engulf the orbit of Jupiter. Now imagine that deep within its fiery heart, instead of a conventional nuclear furnace, there spins a city-sized neutron star. This is not a binary system where two objects orbit each other. It is a star within a star, a slow-motion merger of cosmic extremes. The story of its birth is one of gravitational intimacy and inevitable decay. It begins with a binary pair, a neutron star and a large companion star. As the companion ages and swells into a giant, its outer layers can expand to engulf its dense partner. The neutron star does not vanish. Instead, it begins a long, spiraling descent through the tenuous outer envelope of the giant, like a lead weight sinking through thick syrup. Friction and gravitational drag pull it inexorably inward over thousands of years, until it finally comes to rest at the very center, becoming a new, ultra-dense nucleus. The physics inside such an object would be profoundly strange. In a normal red giant, energy is generated by nuclear fusion in a hydrogen-burning shell surrounding an inert helium core. But here, the core is not inert. It is the searing hot surface of a neutron star. The intense heat and radiation flooding outward from that surface would disrupt the normal fusion processes in the surrounding stellar material. Theorists suggest this could trigger unusual nucleosynthesis pathways, producing unexpected overabundances of elements like rubidium, lithium, and molybdenum in the star's outer atmosphere. This bizarre chemical signature is the telltale clue astronomers search for, A few candidates have been proposed, stars with strange chemical soups that match the predictions, but a confirmed detection remains elusive. Finding one would be a monumental discovery. It would validate a completely novel endpoint of stellar evolution, a hidden chapter in the life and death of binary systems. A Thorne Żytkow object represents a cosmic experiment in layered violence, where the crushing gravity of degenerate matter meets the expansive fury of thermonuclear fusion in a single, unstable body. It challenges our clean categories, forcing us to ask what happens when the universe's most extreme objects are not just neighbors, but become one. At the center of some galaxies, the cosmic violence is not a brief explosion, but a persistent, roaring engine. This is the realm of active galactic nuclei, where a supermassive black hole, millions to billions of times the mass of our Sun, feeds on a swirling banquet of gas, dust, and even entire stars. The immense gravitational energy released as this material spirals inward is not just swallowed by the darkness. A significant fraction of it is converted into a blaze of radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, often outshining the combined light of every star in the host galaxy. But the most extreme manifestation of this power occurs when the black hole's engine aligns its output directly with our line of sight. We call these objects blazars, and they offer us a front-row seat to the universe's most powerful particle accelerators. The physics behind these jets is a masterpiece of extreme magnetohydrodynamics. As matter swirls in the accretion disk, powerful magnetic fields become twisted and amplified, threading the disk like lines of cosmic force. Through a process theorized by Roger Blandford and Roman Zinajic, these magnetic fields can tap into the rotational energy of the spinning black hole itself, acting like a gigantic dynamo. This interaction launches and collimates twin beams of charged particles, protons and electrons, away from the black hole's poles at velocities exceeding 99% of the speed of light. When one of these relativistic jets is pointed almost directly at Earth, its emission is dramatically boosted and its variability compressed into timescales of mere hours or even minutes. We see a lighthouse beam of unimaginable power aimed straight at us. These jets are natural laboratories for physics we cannot hope to recreate. They accelerate particles to energies millions of times greater than what our most powerful machine, the Large Hadron Collider, can achieve. These ultra-high-energy cosmic rays, likely protons, travel across the universe and occasionally strike our atmosphere, creating cascades of secondary particles. Studying blazars helps us understand the origin of these mysterious, energetic visitors. To comprehend a blazar is to push our models of plasma physics and general relativity to the breaking point, forcing us to simulate how magnetized fluids behave in the warped spacetime just outside a black hole's event horizon. These persistent beacons of fury are not merely distant curiosities. They are the universe's way of focusing its most violent and persistent energy into a narrow beam, a cosmic searchlight probing the depths of space and the limits of our physical theories. Even the motion of our own galaxy tells a strange story. We are not drifting aimlessly through the cosmos. The Milky Way, along with our entire local group of galaxies and thousands of others, is on a collision course with a gravitational mystery. Something with the mass of tens of thousands of galaxies is pulling us and everything around us toward a specific point in the constellation Centaurus. Astronomers call this unseen behemoth the Great Attractor. Its immense pull shapes the motion of galaxies across a region of space hundreds of millions of light-years wide. Yet we cannot see it directly. Our view from within the Milky Way's disk is blocked by thick clouds of interstellar dust and stars, placing this colossal anomaly in what we call the zone of avoidance. For decades, it remained a shadowy suggestion in the data, a profound drift in the cosmic current. We now believe the Great Attractor is not a single, impossible object, but rather the gravitational core of our local supercluster, a dense knot of galaxies and, most likely, an immense concentration of dark matter. It is the center of gravity for our cosmic neighborhood, and we are forever falling toward it. But the mystery deepens further. When scientists mapped the motion of distant galaxy clusters using the leftover glow of the Big Bang as a reference frame, they detected something even more unsettling. These enormous structures, each containing thousands of galaxies, appear to share a subtle, coordinated flow toward a single region of space far beyond the Great Attractor. This phenomenon is called dark flow. It is as if a vast, unseen river is carrying these clusters along a course set by something outside our observable universe. This presents a staggering challenge to a fundamental pillar of cosmology, the cosmological principle. This principle states that on the largest scales, the universe should look roughly the same in every direction and be evenly distributed, homogeneous, and isotropic. The Great Attractor and the dark flow suggest there might be imprints on our universe from things we can never see, perhaps from a time before cosmic inflation smoothed everything out, or from gravitational influences of other, disconnected universes in a vast multiverse. These are not just map-making curiosities, they are the largest-scale clues we have, hinting that the story of cosmic structure does not end at the horizon of our vision. They push our models of the universe's origin and ultimate architecture to a breaking point, forcing us to wonder what unimaginable structures or influences lie in the darkness beyond the light. Our own galaxy holds a secret written in high-energy light. Two colossal, ghostly lobes extend from the Milky Way's core, each stretching 25,000 light-years into intergalactic space. These are the Fermi bubbles, immense structures of superheated gas and magnetic fields, glowing faintly in the most energetic form of radiation, gamma rays. They form a vast hourglass shape centered on our galaxy's heart, a silent testament to a cataclysm that occurred millions of years ago. The source of this titanic eruption remains a subject of intense debate. One leading theory points to our own supermassive black hole, Sagittarius A star. While relatively quiet today, it may have experienced a violent feeding frenzy in the past. A sudden influx of gas or a disrupted star could have triggered a short-lived but monstrous outburst, launching jets of energetic particles that inflated these giant bubbles from the galactic center. Another possibility is a period of frenzied star formation, where hundreds of massive stars were born and died in rapid succession, their combined supernova winds blasting material outward in a coordinated galactic-scale shockwave. Regardless of the trigger, the bubbles are a fossilized explosion. They contain ultra-high-energy particles, accelerated by the event's immense shocks, and are threaded with powerful magnetic fields that shape their structure. This makes them a unique laboratory for studying processes we usually associate with distant, active galaxies, but right here in our own cosmic backyard. Their existence pushes our models of galactic ecology or feedback to a new extreme. It shows that even a seemingly quiescent galaxy like the Milky Way has a deeply turbulent history. These outbursts, while destructive, may play a crucial role in a galaxy's life cycle. The energy they inject can heat surrounding gas, preventing it from cooling and collapsing to form new stars, effectively regulating a galaxy's growth. The Fermi bubbles are therefore more than just a spectacular relic. They are a chapter in our galaxy's autobiography, revealing that the quiet spiral we call home has experienced its own moments of violent, transformative fury, forever imprinting its history on the fabric of the halo that surrounds it. Sometimes the universe's most profound messages arrive not as a roar but as a fleeting chirp. Fast radio bursts are cosmic enigmas compressed into milliseconds. In that blink of an eye, a point in deep space can release more energy than our sun emits over 80 years. This is not a slow burn, but a sudden, catastrophic release of power focused into a beam of radio waves that sweeps across the cosmos. When these waves finally reach our telescopes, after traveling for hundreds of millions or even billions of years, they are stretched and dispersed by the thin plasma that drifts between galaxies. This dispersion, a telltale smear across frequencies, is actually a gift to astronomers. By measuring how much the signal has been stretched, scientists can calculate the total amount of ionized material the burst has passed through. In this way, these mysterious flashes act as cosmic scales, allowing us to weigh the universe's missing ordinary matter, the diffuse atoms that are too hot and spread out to be seen by any telescope. The hunt for their source pushes our detectors to their absolute limits, requiring vast radio arrays scanning the sky night after day, hoping to catch a split-second event that could come from anywhere. The leading suspects are the universe's most magnetic objects, magnetars. A starquake on such a dense, magnetized object could theoretically produce a burst of this power. Yet the mystery deepens with the discovery of repeaters. Some sources, unlike the one-off events, fire off multiple bursts in seemingly random patterns. This rules out any cataclysmic one-time destruction like a star collapsing or two neutron stars merging. It suggests an engine that can fire again and again, a reloading cosmic gun. This has sparked a spectrum of theoretical possibilities, from the interaction of a neutron star with a surrounding asteroid belt to the sudden, theoretical snapping of a cosmic string. The most speculative and least likely idea points to engineered signals, perhaps from a civilization harnessing unimaginable power for interstellar communication or propulsion. While this remains firmly in the realm of science fiction, its very discussion highlights how profoundly these bursts challenge our understanding. Fast radio bursts represent a new frontier in time-domain astronomy, the study of a universe that changes in the blink of an eye. They remind us that the cosmos is not a static painting, but a dynamic, flickering display, and we are only now developing the eyes to see its most rapid and secretive winks. The silence of a cosmic void is as profound as any explosion. In the constellation of Boötes lies a region of space so staggeringly empty it has earned the name the Great Nothing. This is the Boötes void, a spherical chasm in the cosmic web nearly 330 million light-years across. If our Milky Way were placed at its center, we would see only a handful of galaxies in our immediate neighborhood, with the next major cluster of stars lying in an unimaginably distant shell of darkness. This is not a perfect vacuum, of course. A few lonely galaxies have been found drifting within it, like isolated ships on an ocean that spans universes. But its density is less than 10% of the average for the cosmos, a staggering underdensity that defies our expectations. According to our best models of the Big Bang and the subsequent clumping of matter, such a vast void should not exist. The universe's structure is a tapestry woven from both dense clusters and empty bubbles, but the scale of the Boötes void seems to push the limits of what that natural process should allow. It is the ultimate negative space, the flip side of a supercluster, and its existence forces cosmologists to re-examine their simulations. How could matter have evacuated such an enormous volume so completely? One possibility is that smaller voids merged over billions of years, like soap bubbles coalescing into one gigantic cavity. Another, more speculative idea is that it might be an imprint of something from the universe's earliest, most chaotic moments, a fossilized defect in the fabric of reality itself. But the void is not passive. Its emptiness has a gravitational influence, with so little mass inside to pull things inward. The space within the void actually expands faster than the universe's average rate. This creates a subtle but powerful push on the galaxies at its edges, influencing the large-scale flow of matter in our cosmic neighborhood. Studying this great nothing, therefore, is a crucial part of understanding the everything. It tests the limits of our theories about dark matter and dark energy, the invisible components that govern the growth of cosmic structure. If our models cannot explain why such a vast emptiness exists, we may be missing a fundamental chapter in the story of how the universe arranged itself. The Boötes void stands as a haunting reminder that absence can be as telling as presence, and that the universe's grand design is written not only in the glittering cities of galaxies, but in the immense, silent deserts between them. Our solar system does not end with Pluto or even with the scattered disk of distant icy worlds. Its true outer boundary is a ghost, a sphere of frozen memory stretching nearly halfway to the next star. This is the Oort cloud, a vast reservoir of perhaps trillions of icy bodies in the deepest, coldest reaches of our sun's gravitational embrace. These are not planets, but primordial planetesimals, the untouched building blocks left over from the solar system's construction over 4.5 billion years ago. They exist in a perpetual deep freeze, so far from the sun that a single orbit can take millions of years. Their hold on our solar system is astonishingly fragile. The gravitational tug from a passing star, or even the gentle push of the Milky Way's tide, can be enough to dislodge one from its slow dance. When that happens, the object begins a long, falling plunge sunward. As it approaches the inner solar system, the sun's heat vaporizes its ices, transforming it into the spectacular, glowing coma and tail of a long-period comet. These comets are messengers from this distant frontier, their elliptical paths tracing back to the cloud itself. We cannot see the Oort cloud directly with any telescope we possess. Its objects are too dark, too small, and too incredibly far away. Its existence is a brilliant deduction, inferred entirely from the orbits of these rare, incoming comets. This pushes observational astronomy to its absolute limit, forcing us to map a structure we can only detect by the rare objects it occasionally sends our way. It is the ultimate proof that our cosmic neighborhood is not a static arrangement of planets, but a dynamic, evolving system with a vast and invisible hinterland. The Oort cloud is our own solar system's breaking point, the frontier where the sun's grip finally fades into the gravitational currents of the galaxy itself. It reminds us that we are not an isolated island, but participants in a much larger stellar environment, one that can reach into our backyard and gently rearrange the heavens with the passage of time. These cosmic laboratories reveal a profound truth about our quest to understand the universe. Each extreme object, from the Magnetars' crushing magnetic field to the silent expanse of the Boötes void, exists at a precise frontier where our current physical theories begin to strain, crack, or fall completely silent. They are nature's own experiments, probing the laws of gravity, quantum mechanics, nuclear forces, and thermodynamics under conditions we could never hope to recreate in any laboratory on Earth. The paradoxes they present are not failures of our science, but its most vital guideposts. The black hole information paradox does not mean Einstein or Hawking were wrong. It signals a hidden layer of reality where quantum mechanics and gravity must finally reconcile. The enigma of dark matter is not a frustrating gap in our knowledge, but a clear sign that the universe is built from something beyond the particles in our standard model. These breaking points are where true discovery happens. They force us to invent new mathematics, to conceive of entirely new concepts like cosmic strings or Boson stars, and to question our most fundamental assumptions about space, time, and matter. The next revolution in physics will not come from a tweak to an existing equation. It will be written in the language of these cosmic extremes, deciphered by the patient observation of how reality behaves when pushed to its absolute limit. Our journey through these 20 objects is more than a tour of cosmic oddities. It is a map of the unknown, charting the very edges of our understanding and pointing toward the deeper, more complete theory that must lie beyond. From the magnetic fury of Magnetars to the profound silence of the Boötes void, Our tour of the cosmos' most extreme objects reveals a universe far stranger and more wonderful than we often imagine. These are not mere curiosities scattered across a distant sky. They are active, violent, and silent experiments running on a cosmic scale, each one a deliberate stress test for a specific law of physics. The Magnetar asks what happens to matter when magnetic force dominates gravity. The black hole pits quantum theory against general relativity in a duel to the death. The dark matter halo whispers that most of the universe's substance is completely unknown to us. Every single object on this list exists at a precise frontier, a place where our equations start to flicker and our confidence wavers. This is not a sign that science is failing. It is the exact opposite. These breaking points are the universe's way of communicating with us, sending signals in the form of gravitational waves, gamma-ray flashes, and ghostly gravitational pulls. They are clues embedded in the fabric of reality, waiting to be decoded. These phenomena are not just pushing physics to its breaking point, they are breaking it open. Each paradox and each unexplained observation is a crack in the wall of our current understanding, and through those cracks we catch fleeting glimpses of a grander, more complete theory. A framework that could one day weave together the immense and the infinitesimal, gravity and quantum mechanics, into a single, elegant tapestry. That is the true promise hidden within these cosmic extremes. Every mystery we solve does not bring an end to the questions. It illuminates a vast new landscape of even deeper mysteries we had not even known to ask. The discovery of pulsar planets forced us to rewrite the story of planetary survival. The detection of gravitational waves opened an entirely new sense with which to perceive the universe. This is the endless driving engine of the human quest for knowledge. It is a journey with no final destination, only a horizon that forever recedes, inviting us further. So the next time you find yourself under a clear night sky, look up. Remember that the darkness between the stars is not empty. It is filled with these incredible natural laboratories. It hums with the vibration of cosmic strings, is structured by invisible dark matter scaffolds, and is occasionally torn by the birth cries of black holes. Every point of light and every patch of darkness is part of a grand, dynamic experiment that has been running for over 13 billion years. We are the latecomers, just now learning to read the instructions. If this journey through the universe's most extreme frontiers has stretched your perception of what is possible, there is so much more to explore. Consider subscribing to continue this adventure into the cosmos's greatest mysteries. And we would love to hear your perspective. Which of these 20 objects do you find the most fundamentally mind-bending? Share your thoughts in the comments below, and let's keep the conversation about our incredible universe going.